the last talk, and Anthony is going to demo his work tonight at the demo reception.
Okay, thanks for the intro. This work I'm going to talk about is Reprise. It's a design tool for specifying, generating, and customizing 3D printable adaptations onto everyday objects. And it's a joint effort between CMU, University of Colorado Boulder, and Autodesk Research. So I want to start by asking you to imagine a drinking straw. Take a few seconds to formulate the image in your head. It's very simple, very ordinary objects. Okay, let's see a show of hands. How many of you are thinking of something like this? I count much less. A minority of you guys are thinking about the curry version of it. Well, in fact, when people first invented the drinking straw, it was just straight. So it's not until 1937 when this guy, Joseph Fryman, realized that his very young daughter had trouble reaching the drinking straw on the dining table, that he had to reinvent these objects, very ordinary objects, and so that his daughter can drink water. So what does story tell us? Universal design is really hard. Even the most common objects you expect to work for everybody might not work for some users or some use cases, such as people might have trouble opening the jar if they have weak strength. Young kids can't reach the faucet unless it's extended. And people with weak coordination might not be able to use even the nail cutter, so it has to be affixed to the table. So although these are very ordinary objects, but if people can use them at a daily basis, they're really limiting the quality of life. And this is becoming more and more serious. According to the Center of Disease Control and Prevention in the US, we are seeing an increasing portion of the population who have at least one basic action difficulty or complex activity limitations. So collectively, I think we should do something about this problem. So let's see how currently we are procuring things we use in our everyday life. So things are designed, massively designed and manufactured, which are then purchased through retail or online shopping. And when it comes to the user's hands, if something doesn't work, the best you can hope for is to return and replace it with something else, and hopefully it would work better or not. And there's really no easy way to go back to how the object is originally designed and manufactured. Fortunately, with the increasingly low cost and available fabrication technology like 3D printing, we can enable a new cycle of procuring, redesigning, and remaking things. Specifically, users can now become the designer and maker. So if something you have doesn't work, there's an opportunity for you to use fabrication machines like 3D printer to redesign and remake that thing. So the main idea of this project is to use 3D printing to adapt everyday objects. And by adapting, I mean mechanically repurposing or enhancing things in user-customized ways. And people are already doing this. If you look at online communities like Thingiverse, you can see examples like, for example, this spray gun that turns a spray can into this gun so you don't have to keep squeezing your bottle when you are painting a large area. Or this thing that stabilizes the drill bit as you try to sharpen it. Or this very simple one-handed bottle opener. But the problem is, if you look at these examples, they are cool, they're cute, but they don't really tell you in general how you can adapt things in your everyday life. So to establish a more systematic understanding of how adaptations are designed, we surveyed over 3,000 examples across online communities and literatures. So first we discover there are several categories of adaptations we can learn from these existing examples. For example, a common category of adaptation is wrapper or extension. It's something that simply wraps around an existing object or an extension that lengthens or expands it, such as this softener for the handle of the buckle of this handle, or our very familiar zipper pull extensions on our backpacks. Another class of adaptation is handle, which is very simple. is a groupable part attached to an object, making it easier to be controlled, to be pulled or rotated. And lever is another class of such examples. It's very specific. It's a bar structure attached to a pivot on an object and making it specifically easier to be turned or rotated. And we also have anchors or stand, a structure with which an object can be stably situated or fixed to the physical environment, usually to support one-handed use. And something that's very interesting we found is this guide, which in this case is a very simple cardboard pieces that basically reduce the visual of the buttons and also serve as the physical guidance, helping people to reach and press these buttons. So we've seen the first design dimension of making adaptations, which is different adaptation strategies. And then we found that for each of these strategies, they correspond to different types of actions of different objects, ranging from static type of action, holding, grasping an object, to linear motion that includes one part, such as pushing, pulling, or pressing objects, to two parts, such as joining or separating object A and B. We also have rotational motion. Again, it has the one part and two part classification. One part meaning you simply rotate a part of the object, or two part meaning squeezing or clutching parts of that object, or two objects. And what we do then is simply filling this design space with examples we found across books and literatures and online communities. And the goal is we can now look at design adaptations in a very systematic way, and we can hopefully use this design space as a lookup table when we try to think of how we can adapt everyday things. So the next step, naturally, is to go about designing adaptations. However, when we go to conventional modeling tools, we'll find that it's still very difficult because most tools, they only deal with geometries without the domain knowledge that the users want to specifically designing adaptations. So to overcome these limitations, I developed a Reprise, which is a tool that in just a few steps, allowing users to explore a range of adaptations, 3D print them, and then installing them in the physical environment. So it's really important to see that Reprise manifests our conceptual understanding of a design space into a simple and executable workflow, which is manifested into a design tool. So to understand how it works, let's look at a usage scenario. So Larry is an occupational therapist trying to help his patient adapting a wire cutter, as that patient recently suffered from hand injuries. So Larry goes to Reprise. So first he specifies a type of action, which is grasping and holding this cutter. A virtual hand helps Larry specify the orientation of grasping, which is then fed into the next step, which generates, in this case, the wrapper that tries to soften the grip of the cutter. And notice that this design can be adjusted, such as Larry can make this wrapper longer, or increase the thickness, or adding small bumps on the surface to increase the grip. And then you can export everything into 3D models, in this case printing into using soft material, and then let the users test the design. So this is good, but it doesn't really solve the problem of clutching the cutter. So Larry goes back to Reprise as a second iteration. He clicks on the clutching option, and in just a few clicks, he specifies the clutching arms of this cutter, and then generate the levers that will reduce the amount of leverage it required to use this cutter. However, this design makes the cutter overall too large to be held in one hand. So the user doesn't really like this design. So Larry goes back to Reprise for the third time, so exploring something different. So he removes off the levers, So now he wants to affix this cutter on the workstation. So he adds this anchor structure. And with a system-supported generation of a pipe clamp, he can easily install the adaptation on the cutter and then install everything on the user's workstation. And now the user can use this cutter in just one hand, and turns out this is the best design amongst all the options. So you can see that Reprise enables a very simple workflow that supports quick design iterations between several adaptation options. And the workflow consists of several simple steps, from specifying the type of action to generating adaptations, to adjusting the design parameters, and then to attaching the adaptation to the object. So in the first step, specifying actions, the challenge is really that geometry itself, as I said earlier, doesn't really have knowledge of how this object is used. So to support this step, the tool provides, for example, a virtual hand that helps specify the orientation of grasping an object. And to specify clutching, the user simply clicks 2 points that defines a plane of clutching, and then another click defines the pivot. So what this step is doing is programmatically describing the type of action with certain objects, which can then be fed into the next step of generating adaptations. For example, to generate a guide for helping the user put a pen into the cap, by clicking the bounding boxes of these 2 parts of the object, these arrows indicate this pen will go into the cap in this direction, and then we simply generate a tunnel that would serve to guide the users to put the pen back to the cap. To generate a wrapper, we generate a bounding cylinder aligned with the user's specified grasping orientation, as specified using the virtual hand. And the lever is generated as a bar that is extended from the object along the rotation arm. To generate anchor or stand, it's basically a cylindrical pier that connects to the rectangular base at the bottom and to the object at the top. So since all these adaptations are generated parametrically, users can then adjust the parameters to fine-tune how you want to use these adaptations. So instead of, in addition to playing with the sliders, the tool can also generate a large number of design options. In this case, the user can select the type of handle he would like for using this fork, and then this allows the user to quickly get that design and then continue to work on it. As a final step, we want to attach the adaptation to the object. So Reprise provides a very simple toolkit, such as the user can cut this wrapper in half so that it can be installed on the fork, or generating very simple beam structures to better support this mark. To verify Reprise, we replicated 15 existing examples, each of which corresponds to a point in our previously constructed design space. So the goal is we want to see if Reprise can enable users to reproduce the existing examples that they already made in our everyday life. For example, this lever makes it easier to squeeze the spray bottle, and this handle makes it easier to open the closet, and this wrapper makes it easier to open the bottle. And the pen can be added with a handle to secure the grip, or this guy for easier to put the pen back into the cap. And some adaptations, such as in this case, can be combined. So this hybrid adaptation has the handle, the guy, and the anchor. And some objects can be adapted differently, such as this handle makes it easier to turn the key, and this guy makes it easier to put the key into the lock. To summarize, universal design is hard, as shown in the beginning example, where a drinking straw, very ordinary and simple object, has to be redesigned in order to support usage for young kids. And it's becoming more and more serious problems, affecting more and more people's quality of life. So in this work, we first come up with the design space by looking at, observing, and analyzing existing examples that describe how systematically how we can design adaptations, which are components that mechanically repurposing or enhancing everyday objects. And based on this design space, we developed a design tool called Reprise, which provides very simple workflow for making adaptations, from specifying the type of action to generating adaptations, to adjusting the design parameters, and then to attaching adaptations onto everyday objects. And the high-level goal is we want to break the traditional cycle of massively designing, manufacturing, and purchasing things to a new model where users can become their own designer and maker, and they can very flexibly redesign and remake things in their everyday life, customizing these things to fit their personal usage. So with that, I'll conclude my talk. I'm happy to answer questions.
All right, we have time for questions. I see one there.
Hi, I was just wondering, one thing that you didn't talk about, unless I didn't notice, is where does the geometry come from for the objects that you're trying to extend?
Yeah, this is a very good question. So in this work, we assume the user already has a 3D model of the object they want to adapt. But in reality, as we make these prototypes and examples, there are several ways you can acquire the geometry. You can either look for the object in online repository or use more and more available 3D scanners. However, admittedly, these solutions are not perfect, so it's still an open question how we can obtain geometry that's good enough for this type of work.
One more question? All right, I have one. So you were talking a lot about people with some handicaps or who just need some temporary help, and personal fabrication basically has the potential to really create like custom one-off objects. Have you thought about like also the health movement, personalized health, kind of integrating some data from the patient to then generate the adaptation?
I think that's a very good question. And when building this tool, we kind of put this step onto the users because we assume users have, such as Larry, the occupational therapist, probably has better domain knowledge than us designers. But it would be great we can come up with models that combine both parts of the world. So working with professionals to encode even more domain knowledge into the tool, that will be a great piece of future work.
All right, let's thank the speaker again.